Well, good evening. Tonight we're going to talk about the relational database model. And of course, this was the model developed by E.F. Codd to simplify database operations. And it was based on set theory and relational algebra, which are two mathematical disciplines. But by applying those in a judicious manner to database technology, Codd was able to come up with a relatively simple method of data storage that has proved to be, that has passed the test of time. It's been around for 40 years and it'll continue to be around into the future. So we're going to look at the various aspects of relational database theory tonight. So a relational database model, it enables logical representation of the data and its relationships. Data is organized into entities with attributes, or for us, we might say it's organized into tables with columns. So a table represents an entity, like a student table. And then the columns are the particular attributes or characteristics we're interested in regarding that entity, such as student name, student ID, student department, and the total credits the student has. Relationships exist between tables. So for example, a student is a member of a department. That is a one-to-one relationship, and that can be represented with foreign keys. Students and classes is a many-to-many relationship. One student can have many classes, and one class can have many students. And that we need a junction table to represent. And we'll be going into this in the next few lectures. So before we go on, let me just ask, what is the difference between a database and a table? Well, a table is a logical structure that represents an entity set, and it's only one of many components of a database. The database is a structure that houses one or more tables and metadata. The metadata are data about data. Metadata include the attributes or characteristics of the data and relationships between the various entity sets or tables. In this slide, we see the characteristics of a relational table. Table is perceived as a two-dimensional structure composed of rows and columns. Each row represents a record of that particular entity, like one student in the student table. And then each column represents an attribute, such as student name. So each one of these student records will have a student name field. The order of the rows and columns is immaterial to the database. And columns have a specific domain. They can be a string or a number, something of that nature. Keys are a very important part of a table because they let us uniquely identify one record in the table. We need to be able to go to a specific record as well as being able to select a group of records. So there's three types of keys that we should consider. One is a super key. So a set of attributes in our table are a super key if the values for those set of fields are able to uniquely identify each row in the table. So, for example, in the student table, there ID is a super key because ID, that one field, will enable us to uniquely identify a record in the student table. Likewise, ID and name combined, those two fields are super keys of student because together we can also uniquely identify each row in the student table. A super key is known as a candidate key if it's minimal. And what that means is there's no fields we could take out of the key set and still be able to uniquely identify a record. So the single field ID is a candidate key because if we took that one field away, we wouldn't have any fields in our key set. And so we wouldn't be able to identify a row in the table. On the other hand, the key set of ID and name is not a candidate key because we could remove name and still use the remaining field in our key set, ID, to uniquely identify a row in the table. We can have multiple candidate keys. For example, a PeopleSoft ID, a Rail ID, or a Social Security number. So we select one of those keys to be the primary key. The one we select is really based on business criteria. Typically, we don't want to use Social Security number because of the risk of identity theft. We want to minimize the use of Social Security number. So we would probably choose something like the PeopleSoft ID. One other key that's related to a primary key is a foreign key. So this is a key in another table that's related to the primary key in the table that we're looking at. So for instance, let's say the primary key in the department table is department name. Now we also have students and instructors who are members of a department. In order for us to match up a student or instructor record with the proper department record, we need to know what department they're in. So we need to have the department name as a field in the student table or the instructor table. That is known as a foreign key, and it references the primary key in the department table. So again, keys are a critical concept in relational database technology. A set of attributes determines uniquely the value of another set of attributes, and that's known as determination. So determination is the state in which knowing the value of one attribute makes it possible to determine the value of another. And it's the basis for establishing the role of a key. And it's based on relationships among the attributes. We also have this idea of dependencies. A functional dependence is the value of one or more attributes determines the value of one or more other attributes. The determinant is the attribute who determines the value of another. The dependent is an attribute whose values are determined by the other attributes. So full functional dependence is the entire collection of attributes in the determinant is necessary for the relationship. So there's, if we look at, for example, the student table, we can say that the ID field is a determinant for the other fields. If you know the student's ID You know the student's name, you know the student's department, and you know the student's total credits. So the ID is the determinant. That's an attribute whose value, once you know it, determines the values of the other fields in the record. On the other hand, name and total credits and department name in student are dependent. They're dependent on the ID of the particular student. So we have this concept of integrity, and there's several types of integrity in our database. One is entity integrity, and that describes a condition in which all the records within a table are uniquely identified by their primary key. The unique value requirements prohibits a null or empty primary key values because an empty key would not be unique if you had other empty keys. Referential integrity describes a condition in which a foreign key has a match in the corresponding table to which it references. So for example, we have to make sure that every department name field in the student table is actually pointing to a record in the department table. If it didn't, then we would try to match up the student to a particular department that wasn't there. Okay, so some of the other things we want to consider are nulls. These are fields with no values. They're empty values, or also called null. So when we create attributes in our table, we can use flags that are special codes to indicate the absence of some value. Not null is one of those, and that's placed on a field to ensure that every row in the table has a value for that column. So in other words, you can't enter an empty field for that particular case. Another thing, a flag that we might want to put on a particular field is unique. And what that means is that there's a restriction placed on the column to ensure that no duplicate values exist for that column. So for a primary key, we would put both a non-null and a unique flag on that particular field. We cannot allow a primary key to be empty, and we have to make sure that a primary key is unique to each record. So let me ask you this. Think about it for a minute, and then we'll have a discussion. Why are entity and referential integrity important in a database? Okay, I think those were good answers. I'll just sum it up. I've turned recording back on. Entity integrity and referential integrity are important because they're the basis for expressing and implementing relationships in the entire relationship model. Entity integrity ensures that each row is uniquely identified by a primary key. So entity integrity means that a proper search for an existing record will always be successful, and that the failure to find a match on a row will always mean that that row that you're searching for does not exist in that table. Referential integrity means that if a foreign key, such as department name in the student table, contains a value, that value refers to an existing record in the other table, in this case, the department table. So Referential integrity ensures that it will be impossible to assign a non-existing foreign key value to a table. Or in other words, let's put it in a concrete example. It would be impossible to assign a student to a department that didn't exist because we made a typo. So, relational algebra is a theoretical way of manipulating the data contents. It's what's known as a procedural language that consists of a set of operations that take one or two relations as input and produce a new relation as their output. There's 6 basic operators. Sigma, which lets you select certain records from a table. Project, that lets you select certain columns or attributes of interest. Union, that lets you join 2 result sets. Cartesian product, which is where each row in one table is matched to all the other rows in a different table. And then rename, where you can rename a table, and set difference, where you can take the records in one table that are not in the other table. So here's the operators. A select operator, again, is going to select certain records. And since records are usually in the horizontal rows of a table, it's a horizontal subset of the table. Project lets you take certain columns or attributes, and since those are usually spread vertically as columns along the top of a table, it's also known as a vertical subset. Union combines all compatible results from 2 different tables, and it excludes duplicate rows. Intersection yields only the rows that appear in both tables. And again, the tables have to be compatible. So the select operation selects records that satisfy a given condition. And that condition is also known as a predicate. So we might have something like select where price is less than $2, and then it's going to go through the records we see in the original table, and it will only select those where price is less than $2. So price less than $2 is the selection predicate. And we also see where you can look at where we select where the P code has a specific value for power drill. So these are relational comparisons, equals, greater than, less than. And we can combine those individual relational comparisons with logical operators and, or, and not to get logical operations that are much more complex. Projection returns a set of attributes or columns in the table. So we're only interested in certain columns, not all of the columns. And so we see here where in our original table, we may want to only show the price, or we may want to only show the description and the price. Think of a instructor table where we have the ID, instructor name, instructor department, and salary. Sometimes we may only want people to see the instructor name, ID, and department. Salary might be considered sensitive, and so we would project just ID, name, and department, and not salary. And here's a union where we join 2 tables together. That means they have the same number of columns, and the columns are compatible. They're the same domain. So that is true in this case. So with the union, we just add the 3 records in the second set to the record, to the bottom of the table. And since there already is a box fan in both tables, we only show box fan once. Okay, so intersect is where we look for records that are in both tables. So looking at these 2 tables, we find that there's only one record, Franklin Johnson, that is in both tables. So the result set from an intersect is going to be Franklin Johnson. The difference operator is going to yield all the rows in one table that are not in the other. And the cross product or Cartesian product yields all possible pairs of rows from the 2 tables. So in other words, we'll take the first record in the first table and match it with each of the other records in the second table, take the second record in the first table and match it with all the records in the second table, and so on. A join is another operation that we do frequently, and that's where we have information that we need to get that is in 2 or more tables. So we have to join those 2 tables together. A divide is one where we will use one 2-column table as a dividend and the other as a divisor. So let's look at joins. Those are the things that are going to be more commonly done. A natural join links tables by selecting only the rows with common values in their common attributes. So for example, we could say, do a natural join on student and department. Well, the student table has a field called department name, and the department table has a field called department name. So only those fields will be considered in the join operation, and the join operation is going to look for a record in the first table with a department name value and match it to that value in the other table. So we might have a student in the College of Business department. So we match up that COB in the student record to COB, the record in the department table that has COB for the department name. And then we join those 2 records together. An equijoin is something that we do that links tables on the basis of an equality that compares specific columns with each table. And then a theta join is where we don't necessarily have to use an equality. We can look for things like greater than or less than. Inner joins are where we only return in our result set the records that have a match between the 2 tables. Sometimes we want to consider all of the records in one table, and if they have a match, then we'll include those parts of the second table in the result set. If they don't, we'll put nulls in. That's known as an outer join. So a left outer join is going to give us all the records on the left of the join. And if there's matching part records in the table on the right, that information will be included as well. So for example, we might have student natural join department. Or let's say student left outer join department. So if we have a left outer join, all the student records will be included in our results. And if student record has a matching department record, the department information will be included as well. If it doesn't, we'll just put nulls in place of that. A right outer join is just like a left outer join, except we include all the records on the right side. And if it has a matching student record, that information will be included as well. So a difference is where we're going to take the records in the first table that do not have a match in the second table. So if the record exists in both the first table and the second table, we don't include them. We only include records in the first table that don't have a match in the second table. So in this case, we can see we have George Jones in the first table, but not in the second. So that record comes over. Jane Smith in the first table, but not in the second. That record comes over. Peter Robinson in the first table, but not in the second. That record comes over. And then finally, Franklin Johnson in the first table, but that does have a match in the second table. So we don't put that in our result set. Last record in the first table, Martin Lopez, no match in the second table, that one comes over. Okay, so here's an example of a Cartesian product, and it's usually denoted by a capital X in formal notation, and allows us to combine information from any two tables. So as an example, the Cartesian product of the relations instructor and teaches is going to be written as instructor big X teaches, or cross teaches. It's big X cross teaches. It's how it's formally read. We construct a tuple of the result out of each pair of possible tuples, one from the instructor relation and one from the teacher's relation. And since the instructor ID appears in both relations, we distinguish between these attributes by attaching to the attribute the name of the relation from which it originally came. So here's two tables that we're going to use in some join examples. And we'll use other tables as well. X divide Y in a relational database means which X has all Y in its general pattern of division. So here, which location has all of the codes in the set A is less than B, and the answer is location 5. So looking at the first table, that's the numerator, if you will, we want to find we're dividing by code, so we want to find a location where code for A has the same value as the code for B. So in this case, A5 and B has 5, A has 9, B does not. A has 4, B does not. C has 6. A doesn't have any of those, and neither does B, and neither does D or E. D has 7. None of the others have those. D and E have 8, but again, we're looking for the ones where A and B have the same value, and that's going to be the second field location that has a value of 5. Well, if we look up that, we're going to return 2 records, one with code A, one with code B. So data dictionary is going to keep all the information we have about our database, the fields in the tables, the domains of the fields, constraints, primary keys. System catalog is usually how a database management system will keep data dictionary in the database itself. We can also maintain an external database to help us keep track of what's going on in our database. And as we've talked about, there's relationships we can have within a relational database, a one-to-many. So example, one department record will have many students, but one student record will belong to just one department. A one-to-one relationship, one entity, one department will have one dean, and one instructor, a record that's a dean, will be associated with one department as that dean in that dean relationship. And then we also have many-to-many relationships, and that is, for example, students and classes. One student has many classes, and one class has many students. It turns out that relational databases implemented as tables cannot handle a many-to-many relationship. They can handle a one-to-many or a one-to-one. So what we do with a many-to-many is we create what's known as a composite table, or it's also known as a bridge table or an associative table. And we create a one-to-many relationship between each of the tables in many-to-many. So for students and classes, we would create a composite table called registration that thereby removing a many-to-many relationship between students and classes. So then we would have a class would have many enrollment records in the registration table. And then likewise, each student would have many enrollment records in the registration table. And that way we can implement it in a relational database. So here's an example again of a one-to-one. One professor in the faculty table is going to be the chair of a department, and a department will have only one faculty member as its chair. Here's an example of what I was saying about we can't handle a many-to-many relationship in a tabular format. So what we do is we create 2 one-to-many tables by putting an additional table in there. So between student and classes, we can have a registration or an enrollment, a junction table between the 2 of them. And one student registers for many classes, and each class has many enrollment records as well. And so, you know, here we've got even more detail where classes or sections are what the student enrolls for. in a particular course. So you've got a course like, say, BADM338, which is a popular undergraduate course, and it may have 3 sections. So one course will have 3 sections, BADM 338, 01, 02, and 03. And then each one of those, like BADM 33801, will have many students in it, and many students will enroll in that course. So data redundancy is, again, something we want to reduce in a properly modeled database. Redundancy not only unnecessarily increases the size of our database, but it can cause update anomalies and other problems. So we want to reduce that, and we will go ahead and use a proper database design to do that. And one of the things we can do is to make sure that each table is about one particular theme. So we've got a student table about students, a department table about departments. We don't have a combined joint table student department that has 2 different themes in it, because we'll have redundancy in those cases. And here's an example that's not from the university database of a relational diagram. This is for an invoicing system. So one customer will have many invoices. And so you see we have a foreign key in the invoice table called customer code. That's the primary key in the customer table. Likewise, an invoice will have many line items, because people can order many different things on one particular invoice. And then the line items will refer to product codes. So a product table will have many line items that refer to it. And so again, we see a foreign key in the line table of product code. And an index is something that lets us speed up the access to certain records by creating pointers to them. Now, we have to be careful with that in transactional databases, because every index we create on a table is another file that has to be updated. So as we create more indexes, it takes us longer to insert or update a record, because we have to not only update the table in question, but all of the associated indexes. We can really have a lot of powerful indexes in tables that are read-only, such as what we find in databases. I'm sorry, in data warehouses. Okay, any questions?